Next topic is subspace, the non-empty subset W, capital W, of vector space V is called the subspace of V if W is itself a vector space under the two operation addition and scalar multiplication defined on V. So when a subset is a subspace, that is W, when W is subspace, suppose W is non-empty subset. If W is non-empty subset of capital vector space V, then and if itself W is vector space, that is W satisfies all the 10 conditions of vector space. When W is itself a vector space under the two operations that are defined on already on V. V is a vector space means V with the two operations called scalar multiplication and addition. Under these two operations, V is a vector space. So, and W is a non-empty subset of this vector space V. So, when W is subspace, if W is itself a vector space, under the two operations, what are the two operations that are already defined on the vector space V? Under the operations, addition and scalar multiplication defined on V, that are defined on V, under that two operations, if W is itself a vector space. So, when W is itself a vector space, if W satisfies the 10 conditions, means W and the two operations, addition and scalar multiplication, with these two operations satisfies the 10 properties, means W means elements of W satisfies the 10 properties of vector space, then we say W is a vector space. And if W is a vector space, as W is subset of V, vector space V, and then V becomes a vector space, subspace of V. So when W is subspace of vector space V, if W is a non-empty subset and W satisfies the 10 conditions of vector space, or that is W is itself a vector space. So this is the definition of subspace. Then this is the characterization theorem on the subspace, that is called necessary and sufficient condition for subspace. Let V be a vector space. The non-empty subset W of V, capital V, is subspace of V, is subspace of V if and only if the number property number 1, for each U and V belongs to W, U bar plus V bar belongs to W, or we say U bar plus V bar belongs to W for all U bar and V bar belongs to W. That is, W is closed for addition. The property C1 is true for the W, and the second property is for each U bar in V and for any scalar K, KU bar belongs to W. That is, KU bar belongs to W for all U bar belongs to W and for any scalar K. That is, this is the C2 property for W. And this is the closure axiom number 2, C2 property. So for KU bar belongs to W for all U bar belongs to W and for any scalar K. That is, W is closed for scalar multiplication. This is the property number A is what? W is closed for addition and the W is closed for scalar multiplication. If these two properties are satisfied by the elements of W, then W is a subspace of V. So this definition says that W is itself a vector space, then W is a subspace. That is, W satisfies 10 conditions, then W is subspace. But this theorem says that if when W is subspace of vector space V, if W satisfies these two properties. And so as far as the example concerned about the subspaces, this theorem is important. So if we have to show that W is subspace of any vector space V, then we have to no need to show that W satisfies the 10 conditions. Just show that W satisfies these two conditions and then W becomes a subspace. Okay. So in order to solve the example of subspace, this theorem is important. We show the W satisfies these two properties, then W becomes a subspace. If you use the definition to example, then we have to show W is subspace of V, then we have to show W satisfies the 10 condition. But this theorem says that W satisfies these two conditions, C1 and C2, then W becomes a subspace. So in order to show the subset is subspace of any vector space V, we have to show these two properties. No need to show the 10 properties. Now obviously this theorem now says that these two properties are equivalent to 10 properties. That is, from these two properties, the 10, we have to prove the 10 properties. That is, these two properties and the 10 properties are equivalent. These two properties are equivalent to 10 properties. And now we have to prove the theorem. Obviously the theorem is a necessary and sufficient condition, or if and only if type. That's why we have to prove the theorem in two parts. So assume the previous part of this if and only if, that is, assume that part number one, assume that a non-empty subset W of vector space V is subspace of V. Our assumption is not that W, a non-empty subset W of vector space V, is subspace of V. And now we have to show these two properties. And W is subspace of V, therefore W is itself a vector space. W is, our assumption is W is subspace of vector space V, and therefore assume that the subset W of vector space V is subspace of V, and therefore W is itself a vector space by using definition. As W is subspace of vector space V, therefore W is itself a vector space, and therefore W satisfies 10 axioms of vector space. As W is a vector space, W satisfies all the 10 axioms of vector space. What are that? And that these A1, and now we have to show these A and B, but these A and B are 2 out of these 10, and hence are true for W. And these number A and number B are the closure axioms C1 and C2, and as W is subspace, W is vector space, and W satisfies all the 10 axioms of vector space. Obviously A and B are 2 out of that 10. That 10 properties are satisfied for W. Out of that, these two A and B are the 2 out of that 10, and hence are true for W. No need to show these two properties. Obviously these properties are true for W because W satisfies 10 properties, 10 axioms, and these two are the 2 axioms out of that 10 axioms, and so these are satisfied for W. Now this is the part number one. Now in part two, part B or part two, we assume that this is called sufficient part. This is necessary part. Now sufficient part. Assume that the condition A and B are holds for W or true for W. This is true for W. We assume this. And now what do we have to show? We have to show, to prove W is subspace of V. In this part, we assume that the condition A and B are holds for W, true for W, and to prove W is subspace of V, that is, W is itself a vector space of V. How can you show W is subspace of V? W is itself a vector space. And how we can show W is a vector space? W satisfies, that is, W satisfies 10 axioms of vector space. We have to show W satisfies 10 axioms of vector space. So the first two, the two closure axioms C1 and C2 are the given conditions A and B, and hence are true for W. So we have to prove the 10 axioms, and out of that 10 axioms, these A and B these are two our assumptions, and these are C1 and C2 property closure axioms. So W satisfies the two closure axioms C1 and C2 are the given conditions A and B, and hence are true for W. Now we have to show the remaining 8 properties. Now we have to show the remaining 8 properties. What are that? The properties A1, A2, A3, A4, and M1, M2, M3, M4. The following properties are inherited from W, from V to W. So no need to prove these properties. These are inherited from V to W. These properties are true for W, for elements of W as the elements of V, as V is a vector space, and that's why V is a vector space. That's why all the elements of vector space V satisfies the 10 properties. And so these 5 properties, what are that? A1, A2, M1, M2, M3, M4. These 6 properties are inherited from V to W, because these properties are, these A1, A2, M1, M2, M3, M4 are inherited properties. these are inherited from V to W. These properties are true for V because V is a vector space, and hence these properties are obviously true for all the elements of W because W is subset of V. So all the elements of W comes from set V, and that's why these properties are true for V. Inherited properties. What are that? U bar plus V bar is equal to V bar plus U bar for all U bar V bar belongs to W. A2 property is U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar for all U bar V bar W bar belongs to capital W. Then K U bar plus V bar is equal to K U bar plus K V bar for all U bar and V bar belongs to W and for any scalar K. Then K plus L U bar is M2 property. K U bar plus L U bar for all U bar belongs to W and for any scalar K. And M3 property, K L U bar is K L U bar for all U bar belongs to W and for any scalar K and L. And M4 property, 1 into U bar is equal to U bar for all U bar belongs to W. So these properties are inherited from V to W. These properties are true for holds for the elements of V. That's why these property are holds for elements of W as well, as because W is subset of V. All the elements of W are the elements of some elements of V. All the elements of W are the elements of V because V is the W is subset of V, and so the elements in W comes from the set V. That's why these properties are A1, A2, M1, M2, M3, M4 are inherited from V to W. So in all, the first two closure axioms are our assumption, and these 6 properties, that is total 8 properties now are satisfied for W. And so we need to verify only remaining 2 properties. Now we need to verify the properties A3 and A4 for W, because all the 8 properties, 6 properties are inherited. 2 properties C1 and C2 are the our assumptions, and that's why it remains to show that the remaining 2 properties A3 and A4 satisfied for W. Okay, so proof of A3 and A4. So the proof of A3. So our assumption is A and B. This is our assumption. A and B are our assumption. So in order to prove the property A3, setting K is equal to 0 in B. What we have, if we put K is equal to 0 in 3, then we have 0 into U bar belongs to W. We have 0 into U bar belongs to W. If you take K is equal to 0 in our assumption B, then we have 0 into U bar belongs to W. And 0 into U bar is 0 bar by using properties of vector space. So we have 0 into U bar is 0 bar. And so 0 bar belongs to W. That is 0 vector exists in W. And this is the property number A3. That is 0 vector must exist in the vector space W. So the 0 vector exists in W. By taking K is equal to 0, we have this in property number B. And in order to prove A4, let U bar belongs to W be any vector. Then setting K is equal to -1 in B. What happens if we take K is equal to -1 in B in property number B? We have -1 into U bar belongs to W. And -1 into U bar is minus U bar, because of the -1 U bar is minus U bar by using the properties for vector space. Already these 4 properties are proved, already seen in the previous lecture, that -1 into U bar is minus U bar. So minus U bar belongs to W. That is therefore negative of every element of W exists in W, because for U bar is any element of W, and for U bar minus U bar belongs to W, that is negative of every element of W exists in W. And therefore for every U bar belongs to W, minus U bar exists in W. This is the in the notation, that is negative of every element of W exists in W. For every U bar in W, minus U bar also exists in W. So this is the property number A4, and hence W satisfies all the 10 conditions of vector space, and therefore W is itself a vector space, and therefore W is subspace of V, because W is a vector space and W is subset of vector space V. Therefore W is a subspace of V by using the definition of vector space, and hence the theorem. That is, this is the second part. So this is very important theorem as far as the exam concerned, that W is subspace of V if and only if these two conditions are satisfied by W. So the equivalent theorem prove that a non-empty subset W of vector space V is subspace of V if and only if alpha U bar plus beta V bar belongs to W for all U bar and V bar belongs to W, and for any scalar alpha and beta. So these two conditions, C1 and C2, are combined here by using this condition, that alpha U bar plus beta V bar belongs to W for all U bar and V bar belongs to W, and for any scalar alpha and beta. Now the proof is again by in two parts. So I assume that W is subspace of V, then W satisfies all the 10 conditions, and then W, then if and as U bar and V bar are any element of W, and alpha and beta are scalar, by condition C1 and C2 combinedly we have, by using condition C2 we have alpha into U bar, beta into V bar belongs to W by condition number C2, because W satisfies all 10 conditions. By C2 property, any scalar and any element of W belongs to W. So alpha U bar and beta V bar belongs to W. And by condition C1, alpha U bar plus beta V bar belongs to W, because addition of every two elements of W belongs to W, condition number C1. And therefore we have the part 1. Now we assume the part, in part 2, assume that alpha U bar plus beta V bar belongs to W for all U bar and V bar belongs to W, and for any scalar alpha and beta. And now we have to show W is a subspace of V, means that is this part, that is W is a subspace of V, that is W is itself a vector space. Then prove the condition C1 and C2, that is for condition C1 we setting beta is equal to 0. In the given condition we set beta is equal to 0 and alpha is equal to then what do we have, alpha into U bar plus 0 bar belongs to W, that is alpha U bar belongs to 0 bar W, and that is the property C2. Setting alpha is equal to 1, beta is equal to 1, what we have, U bar plus V bar belongs to W. So this is the property number C1. So for C1, who can write the proof of C1? C1, that is alpha, take alpha is equal to 1, beta is equal to 1, U bar plus V bar belongs to W. Then alpha, beta is equal to 0, we have alpha U bar belongs to W, that is the property C2. Then write these 6 properties are inherited from V to W, and then write, we need to prove the property A3 and A4. For A3 property, set K alpha is equal to 0 and beta is equal to 0. So 0 bar plus 0 bar means 0 bar belongs to W. We have 0 bar belongs to W, that is 0 vector in W. And for A4 property, for U bar belongs to W be any element, setting K is equal to alpha is equal to -1 and beta is equal to 0, we have minus U bar belongs to W, and therefore negative of each element of W exists in W, and therefore W is a subspace. So write the proof in the 2 parts. This is the first part, right? Second part, proof, second part 2. So this is the theorem. It's called characterization theorem for subspace. So in order to show the subset is subspace of vector space, we have to prove these 2 conditions, C1 and C2 for W. That is, if W is closed for addition and closed for scalar multiplication, then W becomes a subspace of V. So example number 1, these examples are very important as far as the exam concerned. V is equal to R cube, be a vector space under the usual addition and scalar multiplication. We know that V is equal to R cube is a vector space under or with respect to usual addition and usual scalar multiplication. So let W is the subset of R3, like this. W is a set x, y, z, set of 3 tuple belongs to R3 such that 2x plus 3y plus 4z is equal to 0. Then show that W is subspace of V. So what are the condition? What is the condition? That 2x plus 3y plus 4z is equal to 0. So these are the elements of, these elements are elements of W that satisfies this condition. So W is obviously subset of V, and W is non-empty. Clearly W is non-empty. Why is W is non-empty? Because 0, 0, 0 is the element of W. Why? Because 2 into 0 plus 3 into 0 plus 4 into 0 is 0. So 0, 0, 0 is the element of W. So we have at least one element in W, and therefore W is non-empty. W is not equal to 5, and W is subset of V. So no need to prove that W is non-empty. Directly we can write W is non-empty and W is subset of V. So this is the first condition, that when W becomes a subspace of V, if W is non-empty subset of V, satisfying the two conditions A and B. So now W is non-empty and W is subset of V. So this is very obvious that W is non-empty and W is subset of V R3, because W is obviously elements of W are 3 tuple X, Y, Z, satisfying this condition. So obviously W is subset of R3 and W is non-empty, because we have at least one element in W, that is 0, 0, 0 is the element of W. We have also another elements that satisfies this condition, 2x plus 3y plus 4z is equal to 0 are the elements of W. So in every example, write this first sentence this directly, that clearly W is non-empty subset of V. Okay, and then the two would, now we have to prove the two conditions. What are that two conditions? The first condition is what? In order to show that W is subspace of V, we have to show these two properties. What are the properties? U bar plus V bar belongs to W for all U bar and V bar belongs to W. That is, addition of every two elements of W belongs to W. So first take any two elements from W, like U bar is equal to x1, y1, z1 and V bar is equal to x2, y2, z2 belongs to W. Be any element, be arbitrary element from W. So don't take these elements are particular element. When these elements are particular element, if you take suppose U bar as 1, 2, 0, like this element 2, 3, 4, then it becomes a particular element. These are not particular element. X1, y1, z1 and x2, y2, z2. These are the two elements of W. Now what do I have to show? That the addition of these two elements, that is U bar plus V bar, belongs to W. And this x1, y1, z1 is the element of W. What we have? 2x1 plus 3y1 plus 4z1 is equal to 0. Because this x1, y1, z1 or U bar is the element of W, means this element satisfies this condition. 2x1 plus 3y1 plus 4z1 is equal to 0. Also, this x2, y2, z2 is the element of W, and therefore it satisfies this condition. 2x2 plus 3y2 plus 4z2 is equal to 0, number 1 and 2. And now what is U bar plus V bar? That is x1, y1, z1 plus x2, y2, z2 is equal to, how we can add these two elements? Use the usual addition. Definition of usual addition. What is the usual addition of these two elements? X1 in round bracket, x1 plus x2 comma y1 plus y2 comma z1 plus z2. This is again a 3 tuple U bar plus V bar. And now we have to show this U bar plus V bar means this element x1 plus x2 comma y1 plus y2 comma z1 plus z2 belongs to W. So when this element belongs to W, if 2 into x1 plus x2 plus 3 into y1 plus y2 plus 4 into z1 plus z2 is equal to 0, then this element belongs to W. So consider 2 into x1 plus x2 plus 3 into y1 plus y2 plus 4 z1 plus z2 is equal to 2x1 plus 2x2, 3, that you multiply by 3 in bracket, multiply by 4 in bracket. And then write 2x1 plus 3y1 plus 4z1 in one bracket and 2x1 plus 3y1 plus 4z1. And write the remaining quantities 2x2 plus 3y2 plus 4z2. Right here 2x1 plus 3y1 plus 4z1. 2x1 plus 3y1 plus 4z1 right in this bracket, and in another bracket 2x2 plus 2x2 plus 3y2 plus 4z2 in another bracket, and the value of this bracket is 0 by using this 2x1 plus 3y1 plus 4z1 is 0, and 2x2 plus 3y2 plus 4z2 is 0. So 0 plus 0 is 0, and then U bar plus V bar belongs to W, because this U bar plus V bar satisfies this condition, that is 2 into x1 plus x2 plus 3 into y1 plus y2 plus 4 z1 plus z2 is equal to 0, and therefore U bar plus V bar belongs to W. And therefore this U bar and V bar are arbitrary element of this set W, and the condition is true for arbitrary element. So we say the condition is true for all element. Therefore we say that U bar plus V bar belongs to W for all U bar and V bar belongs to W. And the second condition, now we have to show any element of W and any scalar, its multiplication belongs to W. So take, that is the second condition, B number condition. What do we have to show? We have to show this condition, that is K U bar belongs to W for all U bar belongs to W and for any scalar K. That is any element of W and any scalar, its scalar multiplication belongs to W. So let U bar, take U bar is equal to XYZ or X1 Y1 Z1. Any take, we can take any notation. So suppose U bar is equal to XYZ and belongs to W, and K be any scalar. This U bar is any element of W and K be any scalar. Then U bar is equal to XYZ is the element of W, and therefore this XYZ satisfies the condition 2x plus 3y plus 4z is equal to 0, because this XYZ is the element of W, and therefore this XYZ satisfies the condition, this condition of this 2x plus 3y plus 4z is equal to 0. Now what is K into U bar? Is K XYZ, and how you can write the multiplication? We use the definition of usual scalar multiplication. So it is what? Kxyz is kx comma ky comma kz. Okay, and now we have to show this ku bar is the element of W, means this kx ky kz satisfies this condition, 2 into x plus 3 into y plus 4 into z. That is, we have to show 2 into kx plus 3 into ky plus 4 into kz is equal to 0. So consider 2 into kx plus 3 into ky plus 4 into kz. Take k as common. So we have 2x plus 3y plus 4z. And then it is equal to, don't write here suffix 1, because the element is U bar is not x1, y1, z1, is xyz. So write 2kx plus 3ky, consider 2kx plus 3ky plus 4kz, and take k as common. We have 2x plus 3y plus 4z, and the value of 2x plus 3y plus 4z is equal to 0. So by using that equation number star or 3 or 1, so we have k into 0, and k into 0 is 0. And so we have U bar into k into U bar belongs to W, and therefore we have that k into U bar belongs to W for all U bar belongs to W and for any scalar k, because this U bar and k be any scalar and any vector, and that's why it's true for any vector U bar and any scalar k, and therefore we say it is true for all vectors of W and for all scalar k. So k into U bar belongs to W for all U bar belongs to W and for any scalar k, and hence W is subspace of V. So W is subspace of V. Why? Because W is non-empty subset of V, and W satisfies these two conditions. W is closed for addition and W is closed for scalar multiplication, and that's why W is a subspace of V. So here, how you can show the subset is subspace? By showing the two conditions, that is W is closed for addition and W is closed for scalar multiplication. That is, the addition of every two elements of W belongs to W, and any scalar and any element of W, its scalar multiplication belongs to W, and therefore W is subspace of V. So in order to show the subspace, we have to show the two conditions by using theorem. So the next example of again subspace. So we will see the next example in the next lecture.